The landing gear system is one of the most critical and fascinating parts of an aircraft. For most passengers, it is simply the wheels that extend before landing or retract shortly after takeoff. But behind that simple motion lies one of the most sophisticated and heavily engineered systems in aviation. The landing gear does far more than just carry the airplane's weight on the runway. It absorbs enormous amounts of energy during landing, provides steering and braking during taxi, and retracts into the fuselage or wings to ensure the aircraft remains aerodynamic in flight. Without it, no modern aircraft could operate safely. To understand the story of landing gear, we need to go step by step, from its history and design to the technical systems that make it work, and even the rare but dramatic cases when it fails. In the earliest days of aviation, when airplanes were small, fragile, and incredibly light, landing gear was nothing more than a pair of bicycle wheels attached under the fuselage. The Wright brothers' aircraft did not even use wheels, relying instead on a wooden sled-like structure that slid across the ground. As aviation matured, wheels became the standard, and the designs grew more complex. Aircraft quickly became faster, heavier, and more powerful, and that meant landing gear needed to evolve. A simple fixed wheel with no shock absorption was not enough anymore. Engineers developed suspension systems, shock struts, and later, retractable gear that could tuck inside the aircraft structure. Today, landing gear systems are incredibly advanced. Let's imagine a typical commercial jetliner sitting at the gate. Underneath the aircraft, you see a complex assembly of struts, wheels, hydraulic actuators, and brakes. The main landing gear, usually positioned under the wings or fuselage, supports the majority of the aircraft's weight. A typical large aircraft could have 4, 6, or even more wheels on each main gear to distribute the tremendous loads. The nose gear, positioned at the front, has fewer wheels, but provides steering on the ground. Combined, they make sure that when an aircraft weighing hundreds of tons rolls along the runway, the force is evenly managed. The heart of the landing gear system is the shock strut, sometimes called the oleo strut. This ingenious device is filled with hydraulic fluid and compressed gas, typically nitrogen. When an aircraft touches down, the strut compresses, forcing hydraulic fluid through a small orifice, which absorbs the kinetic energy of the landing. At the same time, the compressed nitrogen provides a spring-like cushion, reducing the impact felt by the structure and the passengers. Without this system, even a gentle landing would feel like a violent crash, and the structure of the airplane would suffer extreme stress. Another critical component is the braking system. On a modern jetliner, the main wheels are equipped with multi-disc brakes similar in principle to those on a car, but vastly larger and more powerful. When a jet touches down at speeds of 150 knots or more, the brakes must absorb enormous amounts of kinetic energy. This is why they are designed with advanced heat-resistant materials and cooling systems. Some brakes are carbon-based, able to withstand thousands of degrees of temperature without losing effectiveness. Pilots apply brakes through hydraulic pressure, but modern aircraft also use auto-brake systems, where the computer manages braking intensity automatically based on settings chosen by the crew. Braking alone is not always enough to stop an aircraft in the limited runway distance available. That's where additional systems come in. Many jetliners use thrust reversers, where the engines redirect exhaust forward to slow the plane. But on the ground, the landing gear plays the starring role. Anti-skid systems, similar to ABS in cars, prevent the wheels from locking up, ensuring maximum friction without skidding. Sensors continuously monitor wheel rotation, adjusting brake pressure hundreds of times per second. This allows the aircraft to stop safely even on wet or icy runways. One of the most iconic features of landing gear is its ability to retract into the aircraft after takeoff. Leaving the wheels exposed during flight would create massive drag, slowing the plane and wasting fuel. Retraction is accomplished using hydraulics or, in smaller aircraft, electric actuators. Doors open, the gear folds inward, and then the doors close again, sealing the aircraft's smooth aerodynamic shape. It sounds simple, but the mechanisms are highly complex. The gear must lock securely both in the extended and retracted positions. Failure to lock could mean catastrophic results. Redundant sensors, locking pins, and backup systems all ensure the gear is either fully up or fully down. Steering on the ground is another vital role of the landing gear. The nose gear, connected to the rudder pedals and tiller in the cockpit, can turn left and right, guiding the aircraft along taxiways and runways. Hydraulics provide the force, while the pilots control the direction. On very large aircraft, such as the Airbus A380, multiple sets of wheels can pivot, allowing smoother turns despite the enormous size. Imagine maneuvering a building-length aircraft through narrow taxiways. Without advanced gear steering systems, it would be impossible. But like all complex systems, landing gear can fail. And when it does, the results are dramatic. History has several chilling examples. In some cases, the gear refuses to extend, leaving pilots to prepare for a belly landing. In others, one side extends while the other does not, threatening a dangerous asymmetric touchdown. Sometimes tires burst on landing, creating sparks, fires, or even veering the aircraft off the runway. Although rare, these incidents remind us of just how critical the landing gear is. One famous case occurred in 2005 when JetBlue Flight 292 experienced a nose gear malfunction shortly after takeoff from Burbank, California. The nose wheels had rotated 90 degrees sideways, locking in the wrong direction. The pilots faced a terrifying situation. For hours, the aircraft circled Los Angeles, burning fuel, while news cameras broadcast the drama live. When the plane finally landed at LAX, the pilots managed an extraordinary landing, keeping the nose off the ground as long as possible before the sideways wheels touched the runway. Sparks flew, tires shredded, but the aircraft stopped safely, and all on board survived. It was a powerful reminder of the landing gear's importance and the skill required to handle its failure. Another incident took place with LOT Polish Airlines Flight 016 in 2011, when a Boeing 767 suffered a hydraulic failure that prevented the landing gear from extending at all. After circling Warsaw for hours, the pilots executed a flawless belly landing, skidding along the runway on the aircraft's fuselage. Emergency crews rushed in, and again, everyone survived. The sight of a massive jet sliding without wheels was both terrifying and awe-inspiring, showing how training and preparation can overcome even the worst mechanical failure. Behind every landing gear system is a world of engineering marvels. Designers must account for every possibility: rough landings, uneven runways, crosswalks, winds, icy conditions, heavy loads, and repeated cycles of extension and retraction. Gear must be light enough to not burden the aircraft in flight, yet strong enough to handle impact after impact. Matt.